So this is my wave here. In the next energy level, right, that wave is going to pass through once. What do you think is going to happen to the sign on those orbitals? Should they change?
Yes.
Yes.
Yeah. So this one should be, we'll make that shaded. And it's arbitrary. You know, I'm just shading. I'm not saying what's positive and what's negative. It's just that one is going to be shaded and the other one will be unshaded. Are you following that? And you can keep doing this. The more molecular orbitals you have, the more times the wave is going to pass through zero, and the more times the signs on your p orbitals are going to change. So let's go up into this 4-pi system. Right? If I got 4 p orbitals, everybody agree with that? I have 1, 2, 3, 4 p orbitals. Is that right?
Yes.
Mm-hmm. And so if I have 4 p orbitals, that means I'm going to be able to combine them 4 different ways, which means I'm going to generate 4 molecular orbitals. Right? 4 different molecular orbitals. All of them are going to have 4 p orbitals in them. So I'm just recapping from the video, and then we're going to take this information and I'm going to show you why it's important. All right? So here's one. Excuse me in advance if it's a little sloppy. All right. Following. Yes or no?
Yeah.
4 p orbitals in each one, but each one of these is a molecular orbital. Right? So I have 1, 2, 3, 4 molecular orbitals because I have 4 p orbitals and I can combine them 4 different ways. Right? On the bottom level, the lowest energy level, right? This is what we call a ground state. How many times will a wave pass through zero here?
1.
None.
Actually,
None.
None, right? So this should look like this, right? What does that mean for the signs on your lobes?
They're all gonna be
they're all the
either
same.
It should
or
be
they're all
all good. They should all be the same. All right, then in the next energy level, when I go, because energy is increasing this way. Sorry about that. Energy is going up. Right? What about in the next level? How many times should that wave pass through zero? Keep in mind, did you say 1?
yes.
Yes. The wave is always going to follow the same pattern. I don't care if you got 1,000 orbitals, it's going to follow the same pattern. Right? 0, 1, 2, 3, 4, 5, all the way to infinity. Right? So I'm going to shade that, and then I'm going to shade these. Yes or no?
Mm-hmm.
Then if I go to the next energy level, how many times is that going to pass through? Twice, right? But it's got to be symmetrical. So I'm going to put it here. I'm going to pass it through there. Then I'm going to pass it through here like that. So this is shaded. These two are going to be shaded. And then this is shaded like that. Yes or no?
Yeah.
No, that was a real dry yeah. Yeah. Hurry up, man. Got to eat breakfast. What about here? How many times?
3.
3 times, right? So here, like that. And if you watch the video, this is redundant, but it's also reinforcing. So that's good. Right? Like so.
I have a question though. So you said that the charges of the shaded area aren't like specified. Like we would know that.
You can't know that because you can't know the 2 characteristics of an electron at the same time, right? And that the Pauli exclusion principle. So we can know where it is, but you know it's gonna have a negative charge. So in theory, wherever the electron is, yes, that area is gonna have some amount of negative charge to it. But shaded and unshaded doesn't mean that it's positive or negative.
Okay.
Does that make sense?
Yeah.
Okay. All right. So this is the MO diagram for a 4-pi system. And what does that 4-pi mean again?
It's 2 double bonds, 2 sides to each bond.
Okay, but when I say that, when you hear me say 4 pi, what am I referring to?
It's for
Electron.
I,
4 electrons. That's exactly
Okay.
right. 4 pi electrons. So these orbitals, keep in mind, I said the energy is going up this way, right? So each orbital can hold, what's the maximum number of electrons any orbital can hold? Come on, jog your memory back to your first day in Dr. Curry's class.
What is it, 16 or 32?
Woo, 32. Man, you finna blow the whole universe up.
Hey, just forget about that. Just forget I said it.
It's okay. But you know what though, Johnny? I appreciate you just chiming in. So I'm not
Yeah, I'm
gonna,
trying to.
yeah,
Try my best.
yeah. So any given orbital can hold 2 electrons. Is that right? That's the max.
Yeah.
Is that right?
Okay.
So if we got 4 pi electrons, the way we fill this thing up is we fill up the low energy orbitals first before we touch any of the other ones. So it's the same, all of the concepts that kind of go along with atomic orbitals, they apply to molecular orbitals too, but the molecular orbitals just help us to describe more complex molecules.
What's going on, Slim?
All right. So if that's 2 of my electrons right there, is that right?
Mhm.
How many do I have left?
2 more.
I got 2 more, so I'm gonna put them here. Following? So now this introduces us to another concept. So this orbital right here has 2 pi electrons in it, and is higher in energy than the lower energy molecular orbital. So this one is what we call the HOMO. It's called a HOMO. It's the highest occupied molecular orbital, right? Let me ask you this: we're dealing with atoms. Let's not even talk about on the molecular level. When we're dealing with atoms, right? If you have an atom, which electrons get affected first when it's reacting with another atom? What's that term?
valence.
Valence electrons. Why? Because they are further away from the nucleus. The nucleus is positive. It's got less pull on those electrons, so they're the easiest to influence. Is that right?
Yeah.
They also happen to be the highest in energy too, and so that's why they are so easily influenced, because they're already in a high energy level. So those are the electrons that get donated first. Does that make sense?
Yeah.
So when you're dealing with a molecular orbital type system, if you have these 4 electrons, right? Let me change my color right quick. You got these 2 electrons here and these 2 here. Which one are higher in energy?
The second row.
The second one. What that means is that those are going to be your electrons that react. Does that make sense?
Can you repeat that?
So the high energy electrons are going to be more reactive. So that's higher energy. That means they're going to be more reactive.
Okay.
Just like in an atom, right? The valence electrons are higher energy, so they're more reactive. So when you have a molecular orbital type system, it's the same concept. The high energy electrons are the ones that's going to be more reactive. So the electrons, with this particular molecular orbital, is what we call the HOMO, highest occupied molecular orbital. And then the one above it, I'm going to change the color of my highlighter. I should probably not use purple. The one above it right here, is it filled or empty?
Empty.
It's empty. So that's unoccupied. Is that right?
Mm-hmm.
If we call this one down here occupied, yes. The one above it is empty, so we'll call it unoccupied. So that orbital, that particular orbital, is what we call the Lumo. Let me erase this. This is so much better than writing on a whiteboard.
It is.
And I got all the room in the world. I ain't got to be flipping, moving, turning, erasing,
Hitting the board.
hitting the board. That's the only thing I miss. That's the only thing I miss.
Of
Right?
course.
So this is the Lumo right here, right? The Lumo means lowest unoccupied molecular orbital, right? Are y'all following that?
Mm-hmm.
So highest occupied molecular orbital. So the point I'm making is that any molecular orbital type system is going to react either through its HOMO or its LUMO. That's it. It's not going to react through any of the orbitals. So it's either going to be for the 4-pi system, it's either going to be this orbital right here or this one that it reacts through. Depends on how it's reacting, right? So let me ask you this. If the 4-pi system was acting as a nucleophile, which orbital do you think it would react through?
You said if it was a nucleophile?
If it was acting as a nucleophile, which orbital do you think it would react through?
The HOMO, right?
Yes, it will react through the HOMO. Why? Because
those electrons that's going to make the bone.
that's exactly right. The HOMO is where your reactive electrons are, and nucleophiles do what? They give away electrons, right? Yeah, from part 1 by week 2. And then if it was acting as an electrophile, what do you think it will react through?
Lumo.
The LUMO, because it's empty, right? So the LUMO can accept electrons, right? So let me write that down for you. So the HOMO, right? That's when the molecule is acting as a nucleophile, it's going to react through the HOMO. If it's acting as an electrophile, then it's going to react through the LUMO. Does that make sense?
Mm-hmm.
Yes. Can you